Hello, this is the lesson 10, that's the last lesson, about pressure vessels. So what is a pressure vessel? A pressure vessel is a leak-proof container designed to contain pressurized fluids. It's going to have some pressure internal to it. That's why they call it a pressure vessel. And it can't leak or else it won't be able to hold pressure. So examples, boilers, welding gas bottles, CO2 cartridges, hydraulic accumulators, scuba tanks, anything that contains pressurized fluids. In this chapter, we're going to explore the stresses that are developed in the walls of the spheres and cylinders of pressure vessels. Okay, so in the real world, real pressure vessels have ports to attach pipes and other discontinuities, and these are considered stress raisers. We talked about stress concentrations in chapter 17. Stress concentration considerations are beyond the scope of this chapter, and in this chapter we're only be talking about thin wall pressure vessels. We're going to derive some equations in here when we're talking about average pressure in the pressure vessel. Okay, in which case, thick walled don't apply. We're going to talk about that in the next slide. But a pressure vessel is considered thin wall if the wall thickness does not exceed 1/10 of the vessel internal radius. Now, for all your homework problems, you're going to have to check this assumption that this is a thin wall pressure vessel. Okay, so in this chapter, only thin wall pressure vessels are considered. Pressure vessel is considered thin wall if the wall thickness does not exceed 1/10 of the vessel internal radius. For thin walled pressure vessels, the stress equations are developed considering average stresses. But for thick wall vessels, these equations aren't valid because there is a gradient in the stresses from the inside to the outside. So the average stress that we're going to talk about and derive in this chapter is just not applicable. This is a picture of a pressure vessel. This one's a cylindrical pressure vessel. It has a closed end. And there can be joints in your pressure vessel. In this orientation, you see a longitudinal joint. And in this right here, you're seeing a circumferential joint. And there's different stress implications for the different directions of the joints. Okay, so tensile stresses are developed in the walls of the pressure vessel as a result of the internal pressure. Induced stresses may not exceed the allowable stress, just like the design problems we've been doing this whole semester. Here we're looking at a typical cross-section of a pressure vessel. Internal pressure is applied, and that internal pressure acts radially outward. If we were to consider a free body diagram of this pressure vessel, it's of unit length L, and T is the thickness of the pressure vessel. And so what we have here is forces due to internal pressure is reacted by the vessel walls. Okay, so we have internal pressure acting inside this pressure vessel, and that pressure times this projected area gives us P. That's the force, okay, of the pressure that's pushing on this segment of the pressure vessel. And that force P is being reacted by the sides of the pressure vessel. So here what we have is a tension and a tension over here. Okay, so that TC reacts this P. And then stress is TC divided by L and T. That's the pressure, that's the stress. Okay, here's the force TC. It's divided by this area. The area that TC acts on is L times T. That's the area. If we were to derive this equation, P is the force. That's this force here, P, is induced on the section. So P, this is the force P, equals small p, which is the pressure, times the area. Now the projected area in this case is the inside diameter times the length. So essentially what happens is that this pressure is projected over that area, which is ID times the length here. So therefore, if we substitute that in here, we've got P as our force equals pressure times DI times L. Therefore, the force in the walls is going to be TC equals P over 2. And then if I were to substitute P into this equation, I got TC equals P, pressure, times the inside diameter times L divided by 2. Now, that stress in the wall becomes TC divided by A. That's TC divided by T times L. If I were to substitute this equation for TC in this equation, I get equation 20.1, that the stress, the circumferential stress in the pressure vessel is the pressure times the diameter divided by 2 divided by the wall thickness. And you see when we made the substitution here, we noticed that the L divided out. Okay, so this is how we derive equation 20.1. And that's the circumferential stress, or in other words, the hoop stress. And then this equation here shows you out of the book how that equation is generated. We're going to be using this equation a lot in this chapter. I'm going to end this lesson here and pick it up with video presentation number 2. Thank you.